Good morning. I want to say thank you for coming. And the topic of discussion on my part is going to be talking about linear motion from nonlinear robots. Earlier, there were discussions that ended with linear motors versus rotary motors. So this actually opens up a good segue into it. Typically, when we design robots, one can apply linear motors. Oops, what happened? Oh, never mind. Looking at the wrong thing. All right. So we're basically looking at the Cartesian coordinates and linear axis, or we basically work with the rotary motors with the transmission that translates rotational motion movement into linear motion. And we apply the nonlinear topology to result in a Cartesian plane. So for the purpose of discussion, we will skip the linear axis with Cartesian coordinate because that's very simple. You apply the three axes orthogonally, and then you're basically able to move in the X, Y, and Z plane. So there is not as much of a discussion that I would like to cover on those linear axes, but focus more on the nonlinear topology. Let's talk about some of the examples of nonlinear robots. One of the most common ones in the industry used is a SCARA robot. You also have before I jump into the second one, SCARA typically has a shoulder, then you have an elbow, you have a wrist for the orientation, and then you have a vertical axis, which is your Z axis. So you have a 4-axis, shoulder, elbow, wrist, and then the vertical. You have 2-axis manipulator arm for XY motion. This is one of those ones that allows you to move 2 axes in parallel. You have 1 axis here, 2nd axis here. And having the manipulator arms and pivot points at 2 locations, and the end effector, one is able to produce X and Y motion out of it. The advantage of this is to minimize the space required. If you're using a linear orthogonal axis to produce X and Y, as the axis moves X or Y, there is a workspace, and then there is an additional clearance area that's needed. By taking this approach, you're able to minimize the space required. Floor space is very important. So when you're designing robots, one of the things is how much space is going to be required to put that particular robot on a floor to accomplish the task. Another one that we worked with is concentric robots. So you have 2 circles, and effectively by moving the circle clockwise or counterclockwise on each of the arms, you're able to move the end effector in and out, or if they move in the same direction, you get the theta rotational movement. And combination of the speeds and positions can give you movement within a given radius. So this again minimizes the floor space requirement and gives you the ability, and those typically becomes much more usable if you're going to transfer the operation or the parts from one station to the next station or one bay to the next bay. So that's a concentric frog leg robot. Parallel axis robots, also known as H or T-gantry, and those typically are low-cost robots where you have a serpentine belt that goes through a series of pulleys and allows you to generate motion in X and Y. Delta robots, 4-axis, where you have 3 linkages plus a rotational end effector. Hybrid XY, and the tripod with a rotary gives you all 6 degrees of freedom. You have X, Y, Z, yaw, pitch, and roll. And where you have the X and Y as a conventional stage, the 3 axes of your tripod gives you the yaw, pitch, and roll. Plus you have an additional rotational on the top of your tripod, allowing you to have tool center point control of your robot. You can go into a Stewart platform, 6-axis, literally the workhorse to be able to produce high speed, high forces. And achieve 6 degrees of freedom. Multi-joint articulated arms, typically in a semiconductor fab, you see that more frequently there are the wafer transfer robots, which are similar to ASCAR robots, but you also have ones that actually work at taking a series of wafers from one bath chamber to another one. So you have basically a fork that extends out, picks up load of wafers, transfers that from one chamber or one bath chamber to the next chamber. So these are some of the examples of what we have worked with. Also bevel control, when you're basically working with a robot arm that allows you to create a bevel, being able to move around a surface and control the bevel angle and keeping the edge or the motion path tangent to the path, or the tool rather, tangent to the motion path. Through the discussions, we will go through and talk about what the kinematic equations are for the robots being developed. We also will go through and talk about the tuning optimizations, operations with the filters, and the key is addressing the vibrations. Go through the profile generations, filters on the outputs to the amplifiers, and then talk a little bit about the motion controllers and have you select one solution of centralized versus EtherCAT, and then some of the key parameters or the points when you're selecting the solution. So the very first thing is, based on your application requirement, you have to say what topology is going to be the right one. And there are trade-offs, so we select the topology. Once those topology is selected, then you go through and do the forward kinematics and inverse kinematics. These equations are important because it allows you to transfer from your three-dimensional Cartesian space into the motor space and motor space back into the three-dimensional Cartesian space. An example of a SCAR robot, and something that we will basically talk more about going through it. But here you have, again, as an indicated shoulder and elbow, z-axis, and the end effector rotational for alignment. The kinematic equations, they're needed, and the sole purpose of looking at the kinematic equations, as I mentioned earlier, is to transfer from the motor space to the Cartesian and Cartesian back to motor space. Forward equations would allow you to transfer the motor space into the Cartesian space. So when you power up system, you can basically do initialization one of two ways. You can say, I'm going to do homing of my each axis joint and set a known reference point. You could do that. However, in many cases, you do not have the capability of moving the robot upon power up because there may be obstacles, maybe the potential risk of damaging the mechanics. So using absolute encoders, one can basically know the power position upon power up, and taking that information, going through the equations, and simple trigonometric equations in this particular instance allow them to calculate and know exactly where the robot lies within your XYZ plane. Now, knowing that position upon power up, the next step is, well, I would like to go and reach a certain position. It is very easy to define that space as an XYZ coordinate, but we're not working with XYZ coordinates when it comes to controlling the motors. So we need to transfer that back into the corresponding angular movement that is needed for each of the joints, shoulder, the elbow, z-axis, as well as the fourth axis, which is your orientation at the end effector. Using the equations, we're able to basically compute that, and those displacement calculated for each joint are then used to perform the profile moves as defined. Now that the fact that we actually gone through and defined the topology and calculated the equations for forward and reverse kinematics, next step is to basically look at and say implement the system. If we implement the system, there are the points that are critical are defining each joint, the mechanics, the motors, and because those are already covered and will be covered further with my colleagues Tom and so we will basically skip those particular topics and not go into the mechanical selections or the transmissions and the motor selections and skip through those. Once you have the system, the assumption is that we now talk about integrating and starting to look at the tuning PID parameters. And with the PID parameters, you basically have to look at that and say, select for an optimum response. You want to have a system that's accurate. Ultimately, the purpose of having a robot is maintaining the highest level of repeatability. So the accuracy and repeatability is achieved through optimization of your PID filters. However, the robots change, depends on type of robot. Your inertia changes. As an example, if you have a robot that moves in and out, the reflected inertia, the loading on the motor, and we talked about the dynamic changes of the impedance or the characteristics seen by the motor, those changes, and in order to address those and maintain the accuracy as your loading changes when the arm extends out all the way, we need to have different values of PIDs. Those we can address it one of two ways. We can do it as a piecewise linearization or with a continuous adjustments within the loop. So you can actually define and say how much of an impact do you have, and it's just going to be a function of your gear reduction and transmission. How much of that change when you have a payload and it's extended out versus it's completely retracted, those changes would be reflected back on a motor. And using the different transmissions and gear ratios, you can minimize the impacts because you take advantage of square of the gear ratio against the reflected inertia. So if you have a high inertia, but the high gear ratio would basically reduce the impact seen by the motor itself. So you have the ability to define the relationship and create the one of two options to go in and say, either select the PID parameters at different levels and linearize between those, or you can go in and say, I'm going to define some type of a mathematical function that allows me to control my PID coefficients as a function of theta operation. As the theta changes, I can apply those changes, and the controller allows you to do that. There are other issues that are involved. We talked about the friction. Friction can change the impact of gravity against not just the inertia, but the gravity changes as the arm extends out. Now the lever arm is a lot larger, and you have to apply for the gravitational offset. Also, if there is an arm that basically has a movement that goes over the 90-degree travel, then the impact of gravity and the compensation can basically go both ways. So you need to be able to look at that, and the controller allows basically the ability to address those as part of your frictions resistance that you would have. Spring is one of the component that typically tends to be present when you're designing robots. And when you use the spring by itself, when you look at the relationship F equals Kx, one would define the spring as a linear device. However, when you use it in your system, in a closed loop system, that spring itself brings a nonlinear component, because now your friction or opposing force varies as a function of position. So as you extend the spring, you start seeing a greater resistance. And that means you have to actually continuously compensate for the spring, and you can define that as a function of your position. So compensation for the spring can also be applied into your digital filter that allows you to correct for that additional nonlinear component in that. So we talked about gravity, mass and change of mass or inertia, spring devices. Now, once we've gone through and identified the basic components, we go through, optimize it. When you're running this, you start seeing a vibration. So the robot basically goes through, performs the move, whether it's moving horizontally or extending out. And when you start seeing that vibration, one of the first things is to basically make sure that you eliminate the vibration. Well, how do you do the characterization of the vibration and eliminate that? The very first thing is you bring in the equipment or instruments to characterize that vibration. If the vibrations are seen by the motor, it is a lot easier because you can then read your feedback sensors and it tells you what the vibrations are. In instances when you have sensors, position sensors of dual loop, where you put the sensor position feedback on the load as well as on a motor, you can look at the position of your load and know that you have vibrations. You can characterize the frequency of that. When you don't have the sensor or position feedback on the end effector, how do you actually characterize the frequency? And for that, you basically take the approach of putting accelerometers. Put an accelerometer on the end effector, collect the data, and once you collect the data and analyze that, you at least now have the information on what the resonance frequency is, and if there's one or multiple of them. The controller, the digital filter, gives you the ability to then take that information, and depends on where those frequencies or frequency is located, you can apply a notch, or if it's high enough, just apply the pole so that you're able to still maintain a good system bandwidth and responsiveness and eliminate the potential risk of that vibration in the system. That again is an assumption that actually you're able to see it and the control output is able to filter that out. In some instances, the encoders do not show any type of vibration, but you still have that vibration, and that happens to be at a very low frequency. Well, how do you actually address that when you have no feedback showing the oscillations? And that becomes very critical. So you have to take that frequency that is well below your system bandwidth. And when you're trying to address that, you basically have to go through and say, I'm going to take the profile. And taking the profile, put it through the filter so that I can apply either a low pass and eliminate certain frequencies, or apply a notch on my profile. And that allows me to eliminate a specific frequency or band of frequencies that do not go into the plant. And as a result, you no longer are going to be able to excite the resonance. So you do have an option to go in and apply the filter not only on the output side, but also on the input side on the profile. One of the other option is to understand conditions that applies or that results in the resonances. And in those instances, you could say, when I go around a certain path at certain position, you start seeing the vibration and dies out. So if it is a specific region in which you see the vibrations, one of the other ways is to go in and actually define your motion so that you can actually, from segment to segment, dynamically change the speed and use of the XL and decel, transition to a lower speeds where you're less likely to excite the resonance, and then bring the speed back up as you clear that area. And by doing so, you now have still optimized the motion without excitation of your resonances. So you have various different options that allow you to control. Here's the block diagram of your PIDs. You have a reference generated, and then from the reference generated, you have the PID filters, you have low pass, notch. In some instances, working with the heavier payloads, you may have to dynamically apply feed-forward components. And if you're working with the feed-forward components, whether it's velocity and or acceleration, you also have the ability to change that dynamically on the fly. amplifiers come into play. And amplifiers, the torque ripple, in many times when you're working with the higher resolution systems and you're getting into micron, submicron systems, the torque ripple can contribute to the disturbances. And those can be addressed by looking at the amplifier and say, can I use a linear amplifier so I have a highest resolution and I avoid torque ripple? If not, instead of 10-bit PWM, look at something that offers 16 bits or 12 bits or 14 bits of PWM. Higher the resolution, the quantization step of current from one current level to the next current level is going to be better controlled and it's going to be smoother. So you look at that and say, can I get a higher resolution on my PWM? In order to work with the motors that are load time constant as discussed earlier, you also want to be able to take amplifier that has a high current loop bandwidth so that you minimize the delays. And in this case, look at amplifiers that can basically give you a high current loop bandwidth to be able to work with your high responsive systems. If you're using not servos but steppers, then take a look at stepper motors and trying to run the stepper motors. There are options where you can go in and say, I would like to have 256 microsteps per step, in giving a very high resolution of your microstepping, and you're able to reach over 50,000 microsteps per rotation and ultimately control the level of torque ripple that you may have in the system. So that's another option if you're looking at lower cost and using stepper motors instead of servos. Using stepper motors, there are filters available in a motion controller that allows you to control the frequency and the transition from one frequency to the next frequency to avoid a potential stall or the risk of exciting resonances. So you can take advantage of the step motor smoothing filter, which is basically a low pass applied on the frequency generation path. Now we covered those and we come to the selection of motion controller. There are different thoughts and solutions available in the market. There is a centralized solution and the distributed network solution. In both cases, you have the ability to maintain accurate clock synchronization as it was discussed earlier. In the centralized solution, the advantages are you have instantaneous communications between the motion controller and drive, and you get basically the feedback coming straight into it. You have a common ground between all the components, centralized cabling, and the cost is one of the advantages there. The one thing to keep in mind that if you're going to run the cables between your motors and a motion controller that exceeds about 2 meters, then the cost of cabling may become something of a factor to consider for your ultimate solution. So you look at that, and if your cable lengths are typically less than 2 meters, cost of cabling, running all of the signals back and forth is not going to be that significant, and you might get an advantage with the centralized solution. On the EtherCAT, using clock synchronization is a methodology to make sure that every device connected on that is synchronized to a single clock, a single master clock, I should say. And with that, you have an advantage of running the Cat5 cable, connect to all of your devices as shown here in this little automated view, that from the master, you're going to each of the drives and sharing that information at a millisecond rate and being able to provide the new target positions at a fairly high accurate rate with synchronization. The position is sent back. The encoders typically go back into the drive and then are shared back to the master position or the master controller. And this, I mentioned earlier that the cabling cost becomes significant. So if you're running cable length over 3 meters or more, there are advantages here to be able to use this solution to reduce the cable cost, because then you're running from the master to the drive, typically your power and EtherCAT cable, and all of the other signals that are specific to that axis go into the drive itself. Now, we talked about the what I would call very obvious technical solutions, but then when you're designing a product, you also have a certain amount of responsibility that goes with the design itself, and those are availability of the product. If the product you choose tend to go obsolete in a few year cycle, then you're constantly looking at the design, the verifications, and depends on the application. If it has to go through certification, you have to go through certification again. So trying to avoid those unnecessary work. One of the things you have to keep in mind is how long is the product going to be available. Typically, when Galil offers products, we tend to provide product for a 20-year time frame. So we have an average cycle of 20 years. We have products that we actually introduced in 1988 and was available till 2013. So you had about 25 years of availability on the product. So that is one of the key important element or parameter that you have to select a motion controller that will not force you to go back and redesign the motion control system in a few years time frame. The ability to service the product, we have an average of about 25 years to service the product. Obsolescence of the parts, when that takes place on the product, that becomes our responsibility, not yours, as a system designer. And one of the things that we have done over the last 34 years in the business is provide a plug-in replacement with form, fit, and function if a component on the product goes obsolete. And that's one of the things that we did with our 1988 design of the DMC 630 that continued to be available until 2013. Galil offers about 18 months of warranty. And as Chris had mentioned, we typically work with you with our 100 man years of experience from your design stage all the way through the production cycle. So it's not only just providing this solution and say you're on your own, but our goal is to make sure to build that partnership relationship to make sure that you succeed as you go through the integration. We do one thing that Galil is unique is customization. Over the years, we have done many, many customizations. I would say probably in excess of about 2,800 customizations in the last 30 years. And those include firmware, hardware, and software. We believe that one size does not fit all, whether it's clothing or cars or motion controllers. Everyone has unique criteria, and you basically pick a product that meets about 80% of your motion requirements. And if you need other things to be optimized or tweaked, we're able to offer that both from firmware as well as hardware changes. We do a lot of software customization to work with systems or operating systems that many times are custom OSs or SCADA systems that needs the integration, and we provide the custom solutions for that as well. And lastly, Galil believes in providing the most cost-effective solution, and that's something that comes from the co-founder and the chairman of Galil. And if you're interested, you're more than welcome to visit the website. That pretty much concludes the presentation. I'll take questions. Thank you.
Technology has long been a disruptive force. During the 19th century, the Industrial Revolution altered the world profoundly and permanently. During the 20th century, mass production and electricity reshaped manufacturing, giving rise to large, slow-moving global manufacturers. Today, there are new forces at work, and they're changing the world around us, especially in the field of automation. Thanks to technology, the most successful and disruptive organizations consist of a small nucleus of people with a BHAG, a disruptive technology, and a laser-focused strategy. Today's innovative machine builders and robotics trailblazers are leaping ahead of the competition by thinking big and acting nimbly. As an automation disruptor, understanding what products to integrate into your machine is critical to your success in the 21st century. But with so many emerging technologies, chances are you need someone to help lead the way. That's where we come in. At Electromate, we spend our days helping manufacturers like you build better machines. This is why we exist. Electromate has dedicated teams made up of the best mechanical and electrical engineers in the field. We work in harmony with your engineers to help you design and build custom, high-quality, automated machinery. This is what matters to us. We are proud to offer an extensive catalog of cutting-edge robotic and mechatronic technologies, the combination of which is unique to Electromate. From the harshest conditions above or below ground to the highest accuracy and precision motion control applications, our solutions are unmatched in performance and value. No business is an island. There's no need to fend for yourself. Utilize Electromate's engineering expertise to complement your engineering team and get your product to market faster with less hassle. Our core purpose is to help manufacturers compete globally by building better machines using differentiated automation technology. This is our culture. This is our commitment to you. What's your core purpose? If you want to build a better machine, come talk to us. To learn more about what we have to offer, visit www.electromate.com today. Electromate provides motion control at the speed of technology,